Hey everybody, I put together this Ultralight framework demo project with a few different examples and helper classes to make things a bit easier. I'll have timestamps to skip to parts you might care about and a link to the repository in the video description. Over time, I'm sure some changes will be made and new demos will be added to the repository. As far as I know, this project is in a stable state. If you run into any issues, please report them to the GitHub's repository issues section. I'm also going to have the discussion section open on that repository. For the first part of this video, I'm going to go through the different demos, and then I'll go through some basics of how this framework is set up and each of the individual demos. I made another video in the past for Ultralight 1.2 which explains a basic implementation, so I'm not going to go deep into implementation details that were covered before. Alright, so now with the solution opened, we're just going to make sure the Ultralight demo is a startup project and go ahead and run that. And we've got all of these little different demos here. The very first demo, called the basic demo, it just opens up two windows and they both load up Google, and one of these is using the GPU renderer to draw it and the other one is using the CPU renderer. As far as how they look and everything though, they look exactly the same. The next demo is a Borderless Resizable window. Now, you cannot drag this one around, but you can resize it and it has no border. And if you've ever tried to create a borderless window before, you might notice that this doesn't have that white rectangle bar on the title. And I had to do some hacky stuff in this to make that happen. And I'll have it show up on the screen, the repository I referenced for that, but there was a project written in C that was doing it, and I kind of just copied what they were doing from there and just rewrote it just to be more C++ style. The next demo is a Borderless Resizable Movable window. So it's exactly the same as the last one, except I have added functionality here where I can actually drag the window around. And I just want to emphasize here that this title, this isn't like a normal title bar, right? This is a HTML view, and this is a div, and I have it where when I click on there, it starts dragging. So the next one is for the Ultralight inspector, and it opens up two windows. One loads up Google, and the other one is an inspector based off of the first window. Now, I'm not sure why, but the inspector does take a while to start up. And personally, I don't use the inspector. I try to create all my views where I can debug them properly just using a browser, because I kind of like using Google Chrome for debugging the views. But this could come in handy. I haven't really used it, but this is the demo showing, what it looks like. So this next one is JavaScript C++ Communication Demo. So these first few demos are just JavaScript calling a C++ function and passing in different data types, like passing in a Boolean, passing in null, passing in an array of numbers, key value pairs, which you saw there's like the key is name, age, occupation, and then the values are bill, 50, and then truck driver. This is an example of if you're passing in multiple parameters. This is one where the JavaScript is calling a C++ function that returns back the tick count, right? So it gets back the tick count, and then the JavaScript updates this span with whatever that tick count value was. Now these last three are different because in these, JavaScript is calling a C++ function, but that C++ function calls JavaScript functions. So in all of these, there were no JavaScript functions being called. And in this last one, it was the only one where something actually really got returned. It was returning the tick count. But in these three, the C++ is actually calling JavaScript functions. So this one says, oh, this is a string from C++. This one passes in two arguments, a string and a number. And then this one passes in an array of random numbers. Later in the video, I'll go into how this is all working. But for now, we're going to go on to the next demo. So this next one is an example of an OpenFileDialog. So there's this really plain window that comes up, and there's a button that says click me to open the OpenFileDialog. And this is just a view I made in HTML. And, it's having to get information from the C++ side of things, because you can't really access the file system with JavaScript like this. So, it's pretty straightforward. You select your file, you hit open, or you double click on the file, and then you can get the path back. The next one is an example of a transparent window. Now, I don't have a title bar or anything on this window, so to close it, I have it set up where you can press escape to close it. But you can see this is a transparent window. This guy with 3 teeth. So I can hit escape on that. The next one is showing a different anti-aliasing using the GPU driver. So these are 4 different windows loading the same views, and the only difference is they have a different sample count, but they're all using the GPU driver. So I don't know how well it'll show up in the video, but this first one has a sample count of 1, and you can kind of see the jaggedness of the circles. And this last one has a sample count of 8, and because of the anti-aliasing, it looks pretty good. The jaggedness is not nearly as noticeable. So this next one is, this is a C++ texture being drawn with DirectX, and there's a div in the view. And anytime that the div size changes, it calls the C++ function telling it what its new size is, and then what the position of it is, and then that updates where that C++ texture is being drawn. Now, this was the old way of how you would kind of, have your C++ texture in an HTML view. But now there's actually a much better way, and that's going to be in the next demo here. Well, not in the next demo, it's going to be down here. So we'll get to that soon. The next demo here is just rendering a cube. Now, this cube is not being rendered to an Ultralight view. This cube is being rendered to the render target for this window. And then this at the top is the Ultralight view. So it just is calling a C++ function that is, rebuilding the cube with whatever we select here. And it's set up where you can't have textured and colored vertices. So, it automatically swaps that off if you have the other one on. And yeah, it's pretty straightforward. Now, the next one is the GLTF viewer. Now, the way this works is, obviously you have the rotation speed and then the animation speed if there's an active animation. There's no animations for this model. So you can click this and you see that similar open file dialog. I just kind of copied and pasted it into this demo. And I have some of these GLTF files from the GLTF samples that they have available. So, you can play the animation, and that's pretty much it. Nothing crazy here. But I do have a little GLTF loader I wrote in here, and it uses tiny GLTF. So next for this C++ texture and browser demo. Now, if you're going to have a C++ texture being drawn in your Ultralight view, this is the way that you actually do it. And this demo is set up where if I just click on it, it changes the opacity. But what's happening here is I have an image in HTML, like the img tag, but what's actually being drawn in that image is a C++ texture. And if it's just a static image, then I think it's limited in how useful it is. It's still useful, but it's limited, right? But where it really shines is if you have a texture of a render target. So you see, these are, in my HTML, these are 4 images, right? But these are all referencing different C++ textures, and those textures are based around render targets. And this is where, it becomes really powerful, in my opinion. All right, so before going into all the different demos, I want to review how this framework is set up and some of the implementation details. Every demo is inheriting from the engine class. So there's this engine class, and this is just the base that the demos build upon. The initial demo selection that you see is actually a demo in itself called the demo selector demo. And it has this public variable called selected demo. You can see here where the instance is made for that demo selector. It's initialized while it's running, we get the messages. And then once they select the demo, it closes out. And we can get whatever the demo ID is for what they selected based off that selected demo. Now, if they actually selected a demo, then we'll generate that instance for whatever demo they selected. And then if it doesn't get generated, that's because they didn't select a demo, then we exit the program. If they did select a demo, then this demo instance has been created, and we do the same thing. We initialize up that instance, do the same thing, and then once it closes out, it's a while loop, so we just go back to the beginning, create another demo selector, and keep going through the paces. Now, if we look at this, it's just a switch statement with all the different demos I have, and yep, that's it. Nothing crazy there. For managing the windows, I have a singleton. So inside of this window folder, there's this window manager. And this is what I use if I want to spawn windows or destroy windows. I know a lot of people hate singletons, but for me, this was just an easy way to manage all of this. There's actually quite a few sections where I'm kind of using singletons. So technically, the whole engine class, there should only ever be one instance of the engine running at once, right? And there's this get instance, static method. There should only ever be one instance. If you try to initialize two engines, you're going to get a fatal error and it's going to close at once. It should only ever be one. Similarly, there should only ever be one Ultralight manager instance. There should only ever be one renderer instance, only one input controller instance, as well as one D3D class instance. I have this weak wrapper template for working with weak pointers, just because I don't really like, I don't like calling lock. It seems unintuitive to me, so I just have this weak wrapper, and it works fine. It lets me create one based off a shared pointer or a weak pointer. And the purpose of this is the window manager and the Ultralight manager, they are returning weak pointers. And that's just because, they contain the ownership. And if you want to check if, the pointer you got back is valid, then you want to check if it's expired. And that's how that works. For loading in GLTF files inside of the graphics folder, I have this folder called Easy GLTF. At some point, I might push this out to its own project, so it's just like a separate library being included, but for now it's part of this project. It is actually using Tiny GLTF, and it's just a loader I wrote. It only supports GLTF text format files, so you can't load in GLB files, but I'm sure at some point I'll add in support for GLB. It just doesn't have it right now. I'd like to go through the whole entity model hierarchy for how it's being rendered, but it would be too long for this video, and so I'm not going to go into that here. Now let's start going through the demos. So the first demo was this basic demo, and I have 2 windows and 2 views. You don't really have to store these. I'm just storing it, just for clarity. But yeah, there's no reason in this specific demo that I should really be storing weak pointers to any of these. But I have my window for the GPU view, CPU view, and then my Ultralight view for the GPU view and CPU view. So if we go into the startup, this is called, when the instance is created, or when it's initialized. When initialized is called, we have the URL that we want to load. Whenever we spawn a window with the window manager, we have to pass in the window creation parameters. So this is pretty self-explanatory here. Then with the view, same idea. When we want to create an Ultralight view, we have to create Ultralight view creation parameters when we pass it in to create Ultralight view into the manager. Now for this parameter is important. If you want to use GPU rendering, you need isAccelerated to be true. Otherwise, you set it to false. If you set it to false, the sample count's irrelevant because this doesn't really make sense in the context of using the CPU renderer. You'll see that whenever you spawn a window with this framework or create an Ultralight view, you want to check if it was actually created properly. So you want to check if that weak pointer is expired or not. And then after the Ultralight view is created, you just load in the URL. And then to set a view to a window, you need to call set view to window and pass in the ID of the view and the ID of the window. Now about that, There's one other thing I forgot to mention. There is like every window and view should have a unique ID, right? So when the window is initialized, there's this ID pool manager, and the views have the same thing. They have their own ID pool manager, and it just ensures that the windows and views are all going to have a unique ID. So back to the basic demo. After the GPU rendering window and view are created, then the CPU version is created, and it's the exact same setup. It's just the only difference is accelerated. It's going to be false, and we're not setting the sample count because that part's irrelevant. Another thing I forgot to mention, this force match window dimensions. What this will do is it'll make it so when the window's resized, the view will automatically be resized as well. Let's see, is there anything else for the basic demo? Now, this is where if I want to call some C++ from Ultralight, I will call an event in my JavaScript, but that's not happening in the basic demo, so we'll look at that in a different demo. But that is right here is where this callback would be happening if it was happening here. This framework's set up in a way where when a window is to be destroyed, before it's destroyed, when the destruction starts, this callback occurs with the window ID. When the window has been destroyed and it's done, then this callback occurs. So I have it so as soon as you try to close a window, it just says, okay, we're going to destroy all the Ultralight views. We're going to destroy all the windows. It's important that you want to make sure that you destroy any Ultralight views associated with a window before destroying that window. And then right here, once a window is finally destroyed, we just see, okay, were all the windows with this demo destroyed? If so, set running false, which will make this demo end. Now for this next demo, it's a little bit more involved. So this is for the Borderless Resizable demo. And if I go to the top here, you'll see I create a window, and for the style, I use Resizable and no border. And then I load in from my samples directory, the borderless window HTML. So I'm going to go ahead and open that. And the way that this works is it'll look for this web directory, and it is currently set up where it will check in the executables directory as well as one directory up to try to find the web directory. And the web directory is where all of your custom Ultralight views should be stored. It's also where that inspector is stored at. So if I go to samples and I go to borderless window, I'm going to open this up. You see, this is the HTML for that window. So we've got the div for that top title bar that you see. And you see that when you click on it, I'm calling a function called call event, which every view is going to have access to this with this way that this project's set up. And I'm passing it a string. This is going to be the first parameter is always the event name. So I'm saying, okay, I want to start dragging the window. And then when you double click, I want to maximize the window. I also have an image with that cancel icon that when you click on that, it closes the window. So let's go ahead and look at that again real quick. So this is that div where when I click on it, it highlights it. And actually, I know that this demo we're looking at doesn't support this event, but I am using this same HTML for both of those demos. So that's why this on mouse down is here, even though it's not actually supported. However, the double click to restore it is supported. So let's take a look at that. So on double click, call event, maximize, restore. So I'll go back into my code here. And what I want to look at is the on event callback. So what you do is you can get the actual view that this happened with based off that view ID from the Ultralight manager. So this is just making sure that that view is still valid, which it always should be. And then you see the second parameter here is the event name, and then all the extra parameters come afterwards. So if the event was request title, then we pass in whatever the title was. And that's just because I was using the same HTML for both of these demos. So I just made it so I can set the title this way. Here we have, if they close the window, then we get the window for that view, or we get its ID, and then we get the window from that window ID, and then we can force that window to close. Next, this is what I wanted to take a look at, the maximize restore. So we get the views window, and well, we get the ID of the window for that view, and then we get that actual window. And if it's maximized, we restore it. Otherwise, we maximize it. That's all the real functionality this specific demo has. Let's take a look at the JavaScript for this, because there was that request title. So what happens is, once the window is loaded, I'm calling this event request title, which, as we saw right here, request title's right here, and it returns back a string. So it returns back this borderless resizable demo. So that's stored in title now. And then I'm just getting the span on my HTML, and I'm setting the text to be that title. And that span right here, let's see, span title, that's what's right here. And I believe that's everything. The only other things are, so whenever a window is destroyed for this demo, we are getting the window that was destroyed and destroying all views linked to that window before the actual window destruction continues. And then once that, since there's only one window, once a window gets destroyed, we're just setting this demo to not be running anymore. Now for the next demo, it's the same thing, except it's movable. And it being movable actually makes it quite a bit more complicated. I have it set up where I have a struct with the window drag info for if a drag's in progress, where did the drag start, and where did the window start, as well as which window is being dragged. There's also something with this demo where I'm needing to override the way that the input gets processed, because this is how the input's normally processed for that engine class, where, okay, we get all of the mouse events, and normally, we'll try to dispatch them out to the view. And same with the scroll events and the keyboard events. Well, the difference here is when there's a mouse event, if the drag is in progress, then we want to prioritize, handling that drag. And then, of course, if it's a mouse up, then we're ending the drag and resetting what window's being dragged by setting it to an empty weak pointer. If it's a raw mouse move, then we're getting the cursor position and then recalculating where the window should be based off of where the drag started and where the cursor is right now. I believe the only other difference besides that addition to the process input is where the begin window drag happens. So when that event's called, we get the window, and I really should be making sure that's not expired. So I was putting a cert there. So you can only drag it if it's not maximized, right? So if it's not maximized, then we get the cursor position and we get the window position with get window rect, and then we can set all of the drag info. The next demo was for the inspector. Now for the inspector, it's actually pretty simple, what I remember. So I create the main view, which is Google, and then I create the window. Whoops. Okay, so I create the window, and then I create the main view for the Google view, and then we create the inspector afterwards. So we create a window just like normal. And the difference here is when we create the inspector, we need to set the inspection target for the creation parameters. And that tells it, hey, this is going to be an inspection target. This is not going to be a normal ultralight view. And there's nothing else special happening here. The only thing is that when window destroy start callback happens, I want to make sure that the inspector is always getting destroyed first. And that's just because I had some issues when I would destroy the view first and not the inspector. So this next one, the JavaScript C++ Communication Demo, this one is actually going to be a bit more involved because now we're talking about passing parameters back and forth. Now, I have this wrapper class I made called EasyJS Parm, and it's supposed to make it easier to, pass more complicated data back and forth, whether that's arrays or tables or I guess they're called objects in JavaScript, but like a Lua table or just multiple parameters. So I'm going to go ahead and open up the HTML and JavaScript here. So the HTML, it's really, basic. It's just a bunch of buttons that have function calls like JS, CPP1, CPP2, etc. for all the different demos. So I'm going to go into the JavaScript and see what they look like. So for CPP1, when this event is called, it's passing in the number 5. And in the C++, we say, okay, did we only get one parameter? Because we're just expecting that one parameter, that's that number 5. And then we're making sure that the type is a number, because it should be a number. And then we get the number by calling as double on that parameter, on the first parameter. And then here I'm just storing that in the string and then showing it with a message box and then returning empty JS parm back. The other examples here I think are pretty self-explanatory, so I'm not really going to go into those. We just have a string example, a Boolean example, null, passing in null, passing in an array. So I'll go into the arrays one. For the array, we're getting back one parameter, and it is the array. So let's see what the JavaScript looks like for this. So we create the array here, and then it gets passed in. So if it is an array, then we need to cast it as an array to a vector of JS parms. And then we can go through all of the entries. We can see, okay, make sure it's a number, because I was just expecting an array of numbers. And then I'm building this string, and then I am having a message box with that string. The next one is for a key value pair. And the way it works is, if the data type is a table key value pair, which that's just what I'm calling it, I guess it's really an object. But then what you're going to do is you have to cast that parameter, which in this case there's only one parameter, cast that parameter as a key value pair table. And a key value pair table is a vector of pairs, right? Where the key is a string and the value is another EasyJS parm object. And then I just have a for each loop here going through all of the key value pairs, and then gets the key is always a string, and then I have to determine what the value type is. So if it's, I'm not really handling array, I'm just putting array data here because I would need another loop to go through that. But yeah, I just have Boolean, null, number, string, and then same idea with table key value pair. I'm not handling if it's a nested one here, just because, technically it could just keep going forever, right? And I didn't want to make this part I didn't want to put too much code. It's already a lot of code here. Once that whole string's built, it's just printing it out with a message box. For example 7, it's just real simple, passing in 2 parameters. So this time, the first one is a string. So on here, we assert that we got back 2 parameters. The first parameter is a string, second parameter is a Boolean, and then just building in a way to print that back to the user. And then here, there's something, I guess because the issue here is that this overflows every 49 days, but I don't really care for this demo. I'm just going to leave it. This is where I'm returning a value back from the event. So in JS Cpp 8 demo, you'll see it is calling that event, and it's getting back the tick count, and then it's populating this span with whatever that tick count was. For the last 3 examples here, we're actually going to call JavaScript from C++. So you see here are the 3 JavaScript functions that are going to be called. But if you're wondering, okay, well, how are those events getting triggered? Well, inside of the HTML here, I'm just calling the events here, right? So this one calls CPP.js1. So this event gets called with no parameters. And what it does is it calls this JavaScript function called CPP.js1, and it passes in a string from C++. So we'll go into this. So here's the string that gets passed in, and then that span just gets set to whatever gets passed in. Notice that there is EasyJS parm to store whatever the return value is, if there is something that gets returned. And there's also a string to get what the exception was, if there was an exception. In this second example, it's just passing in 2 parameters this time. So you see parm1, parm2, and it passes in hello from C++ and just a number. And then in this last example, this is where an array is being built. So in JavaScript, it's expecting the numbers array, and then we go through the array, and then we append it all to the span. And then in C++, it is creating a vector of EasyJS parms because we need to store the array as one of the parameters. And then we are pushing back all of those. And then the way it works is there's an issue. I don't know if this is an issue with how I wrote this or what, but if I just passed in this random numbers vector here, it thinks that they're all different parameters. So for it to know that they're all their own parameters, I actually have to create a new EasyJS parm object and pass in that vector. And that's saying, okay, this parm is that array, right? Whereas if I just pass in this array, they'll each be their own parm, all of these different numbers. So that's why I'm doing that right here. For the OpenFileDialog Demo, there aren't any new concepts as far as this framework goes with what's going on here. There just are some additional things like I'm getting my different drives and I'm sending them over. I have this lambda for adding a quick access path. And this is for like adding the C drive, the D drive, and all of that. So you see for all the drives I get from my get list of drives function, this directory helper singleton, I am calling the JavaScript function to add a quick access location where I pass in the drives. And there's some other communication here for the different directories, as well as, for passing in all the files in a folder. But that's not really related to how this project is working. That's just, that's just normal C++ stuff. Next, for the transparent window demo. So the way that this works is just when you create the window, I have the no border and the transparency allowed styles. And then when this close window event gets called, I'm closing the window. Now to actually call that, I have in the JavaScript, when a key is pressed, if they press escape, then I call the event close window. And that's all that's really happening there. So it's a fairly straightforward demo with this. Next, for the CubeDraw demo, the way that this works is we create the window in Vue just like normal. And, we have our CubeDraw HTML here. Then for this, since we're actually drawing to the render target, we have to create a scene for an entity to be in. So we create a scene, we create a camera because the render target has to have a camera assigned to it to know, how to draw. Like, it has to be able to have the perspective and view matrices, so it needs a camera. Then I'm just initializing the projection values, the aspect ratio, setting the position of the camera, and then I'm setting what scene that camera belongs to. Next, I get the render target from my window that was created, and then for that render target, I can set which camera that render target's supposed to be using when it's drawing, 3D stuff. Then I just create a cube entity, and in my scene, I add that entity to the scene. And my scene is really just, it's the most basic implementation of a scene that you can think of. I don't know why I can't open it, but it is a vector of pointers of entities. Now for the generate cube entity, let's see if I can get into this. There are, I have it set up where I can just pass in some mesh generation options. Those are just for, do I want colored vertices, the default where it's white, or the textured vertices? I just have some mesh generator helper class where I generate the cube. If it's wireframe, then I override the pipeline state that's being used for the materials so that it's wireframe. Then I just create a model. I add the mesh for the cube, and then I create a new entity, and I set the model for that entity, and then it gets returned. To handle the rotation for the cube, there's this on pre-render frame virtual function you can override, and I'm just getting the delta time here, and the delta time is just the time between the frames in milliseconds, and then determining how much I want this to be turned, and then I just change the yaw, and I create a quaternion, and then set the rotation for that cube. For the cube mesh options update, this is just a callback from the JavaScript where it'll pass in 3 booleans for the wireframe, colored vertices, and textured vertices. And then that will generate a new cube based off of what is passed in. Next, for the GLTF viewer, Now this has a lot of stuff copied from the OpenFileDialog example. It also has, the same on pre-render copied from the cube, so we are rotating based off the rotation speed. Now down here, we're going to try to skip some of this OpenFileDialog stuff. So when a file is picked, it tries to load that model. That's the main thing that we care about here. After the model gets loaded, then we update the animation list, which is why we have the buttons on the left for selecting the animations. So in here, we're just creating a vector of JS params. We are getting all the animations from that model, and we are sending it over to the Ultralight view by calling this JS function. Let's take a look at the load model function. So the model is initialized, pass in the file path, and then there's this out variable that will give us an error message if something went wrong. And so, if something went wrong, this will be populated. Once we get back the model, then for the entity, we update what the model is by calling setModel, update the animation speed, update the AABB associated with that model, and then we reposition it based off the AABB. There's something wacky about this. It kind of works. I don't know. There's something wrong with this. But for now, this is fine for this demo. The last thing is if someone tries to play one of the animations, that gets updated. So right here, there's this callback for play animation. And so if they call that event, they pass in a string with the animation. Then we go through the animations here. If the animation name matches, then we set that animation clip that's active to whatever that animation name was. All right, so for the next thing, this C++ texture in browser. Now this is really useful. What I'm doing here is I create my window, and then I create a texture. And for that texture, I'm going out to my assets directory, which is it's in the same spot as that web directory. So it's called assets. And I'm getting this image, and I'm going to use that for my texture, the AI Bowser one. Now for this to work, there's a couple things to consider. First off, you have to be using GPU rendering. You cannot do this with a CPU renderer. And we have to reserve a texture ID in our GPU driver in Ultralight. So we have to get the GPU driver from our manager. So this is getting that driver. And then we want to figure out what the reserved texture ID is. So we register a custom texture and reserve the ID, and we pass in the texture for this. Once we've got a reserved texture ID, then we need to create an image source in Ultralight. And the image source is going to say what the texture's default width and height are, what that texture ID is, and what the bounds. I don't know, why you would, but you can change the UV coordinates you're using here. I'm just using 0 to 1 because I want the full texture. Next, you're going to get the image source provider from Ultralight, and then you're going to add this. Now, you need an identifier, so I called this AI Bowser, and then you pass in the image source that contains information for where that texture is, the width and height and bounds. Now that I've registered that image source, I can create my Ultralight view. So I create that Ultralight view, and let's take a look at that. So in this Ultralight view, I've got my div called CPP texture container. And in my JavaScript, what I do is when this gets loaded, I'm dynamically creating an image, and I'm saying, all right, create an image for AI Bowser. And inside of this, it's creating an image where the source is going to be AI Bowser.ImageSource. So it's like, image source equals AI Bowser.ImageSource. And Ultralight, when it sees .ImageSource, it handles this differently than when it handles an image. So the way that this works in Ultralight is it expects you to have a file with .img src extension, and the format is like img src v1, and then the next line is the identifier, which in my case is that AI Bowser text. Personally, I don't see any reason to have files for this. So what I actually did was I put in my own file system implementation here. And in the file system implementation is where I'm handling this. So what I'm doing is when a file is open, or when I'm checking if a file exists, I say, okay, is it an image source path? Yeah, it always exists, right? And when a file is actually opened, if I can find where I'm doing that, right here. So when a file is actually opened, I say, okay, is this an image source path? If it is, then I'm just building the data that I expect in it, right? So the data that I'm expecting, if the name is AI-Bowser.png, then I want that second line to say AI Bowser, right? So this function I have that checks if it's an image source path will also extract the alias. So it would extract this AI Bowser here. So when I build this data, it would be building what I'd be expecting in that file. And then I'm allocating a buffer and then copying this string to that buffer and then passing in an ultralight or returning an ultralight buffer because that's what this function expects to return, returning an ultralight buffer with this information. I hope that makes sense. But the purpose of this was so that I don't have to create a file that ends with .img src with, you know, it would literally look like this, right? So I'd have to create, you know, some file. It could be called, you know, anything, but the text inside of it would have to be this. And so I was trying to avoid that. All right, so let's go back to that demo. And I actually had to add in this destructor. And what this is doing is it goes out to the image source provider from Ultralight. It tries to get the image source with that alias that we had created before. And if it gets it, if it's null pointer, that means it was never actually registered. So if we get it back, what we are going to do is we're going to get that texture ID that we had reserved earlier because we need to manually delete that from the GPU driver. It won't get cleaned up otherwise. It'll just sit out there forever. And then after we destroy that texture, then we can remove the image source. The last example is the multiple embedded cubes demo. And you'll notice something different about this one is we are storing the image sources for each of those render targets. So I'll create this, go back into here. So each of these has their own image source, and I'm storing all of those. Now, the reason that I'm storing those is because an image will only get updated once it gets invalidated. So inside of this, what I'm doing is on the pre-render, when I update the rotation for all the different entities, I am invalidating all of the image sources because otherwise it will not be automatically redrawn. There'd have to be something else to trigger a page redraw in order for that to actually be redrawn. So that's the purpose of invalidate here, so that we can call it anytime that we want that image source to be updated. Other than that, this is where they are being created. So there's just a for loop, says there's 4 of them, 0 to 4. And then, you know, I have a switch case so that they can all be different. And then the entities get created. The difference here is when I am registering that texture, I'm actually getting the texture from my render target. So I'm needing to create 4 different render targets, and then I'm passing in those render target textures to when I create the image source. Something else is, in order for those render targets to actually get rendered when when it does every single frame draw in this framework, what I'm doing after I initialize those render targets is I'm needing to set them up to actually be rendered to. So you'll see here, I create the render target, trying to remember where I did this at. Oh, here we go. So there's this off-screen render target containers. So every render target that you want to draw that isn't a part of a window has to be put into this array in order for it to be drawn to every frame. I think that's everything. At least everything that I'm going to cover in this video. If you have any questions, feel free to leave them in the comments. And thanks for watching, and I hope this is helpful.